This section explains the chapter's structural primitive. Architecture is cache management for a primate brain. Nystrom defines coupling operationally. Two pieces are coupled when you cannot understand one without the other. Good design therefore minimizes the knowledge you must page into wetware before a change becomes possible. Every pattern in the book is then an instrument on one trade-off surface, spanned by 3 speeds. Long-term development speed comes from decoupling. Runtime speed comes from optimization, which encodes assumptions and calcifies. Today's speed comes from slapdash code. Flexibility and performance sit at opposite ends of that surface because one removes assumptions and the other feeds on them. His resolution is sequencing. It is easier to make a fun game fast than a fast game fun. Stay flexible until the design settles, then harden. A command is a reified method call. That is Nystrom's own tagline in Chapter 2. And the whole chapter is that one move unpacked, take a verb. The program performs and thingify it into a noun the program can hold. Once an action is a value, everything a value affords arrives free. Stored in a variable, and your controls become rebindable. Hand it a receiver, and any actor becomes drivable, the player and the monsters alike. Keep it in a list, and you have undo stacks and replay streams. In a language with first-class functions, the pattern mostly dissolves into closures. The class-shaped version earns its keep only when the call must carry state beyond the call, an undo mirror above all. The boundary of the pattern is this: reify the request, never the requester. This section explains the flyweight pattern at the level of its single structural move. Factor an object state by what varies per instance and what does not. The intrinsic part, what Nystrom calls the context-free stuff, such as a tree's mesh and textures, is identical across thousands of instances, so one copy serves them all. Each instance keeps only its extrinsic residue, position, tint, scale, plus a reference to the shared core. A forest of heavy tree objects collapses into one tree model and thousands of featherlight records. The pattern is pure efficiency, and that intent separates it from type object, which shares state to shrink the class hierarchy. GPUs bake it into silicon as instance rendering. Nystrom notes it may be the only Gang of 4 pattern with hardware support. This section explains the observer pattern at its first layer. The whole pattern is one inversion. The subject that does something interesting holds a list of strangers and calls on, notify on each. The move is announcement without acquaintance. Nystrom's achievement example carries it. Physics announces that this thing just fell. Do with that as you will. And the achievement system, registered but never named in the physics code, hears it. Mechanically, it is nothing but a walked pointer list and a synchronous virtual call. No queue, no allocation, no message objects. The reputation for being too slow belongs to its cousins. The price is real though. Coupling moves from static text to runtime list contents. So use it between unrelated lumps of a program, never within one. The boundary is exactly where you stop wanting to read both sides at once. This section explains the prototype pattern, which arrives as a demotion with a rescue. The Gang of 4 pattern puts a clone method on every monster, so that one spawner stamps copies of an exemplar. This buys nothing. Writing the clones costs as much as the spawner classes it deletes. Nystrom admits in Chapter 5 that he honestly cannot say he has found a case where he felt the prototype design pattern was the best answer. What survives is the concept underneath, exemplar plus delegation. New things are defined as deltas off a concrete instance, where a class-based design would define them as instances of an abstract class. The idea fails as a code pattern. It half fails as a language paradigm, in Self and in JavaScript's classy retreat. It wins cleanly in data, a prototyped field in JavaScript's classy retreat. It's C. This section covers the singleton pattern, the book's deliberate anomaly, the one pattern taught, so you will stop using it. Nystrom's compression of the Gang of Four definition reads, ensure a class has one instance and provide a global point of access. That sentence is two guarantees welded together at the word and almost every use wants only one of them. Single instance is a real constraint. Nystrom's example is a file system wrapper coordinating asynchronous operations. Global access is just a global variable wearing a class, coupling from anywhere, invisible dependencies, costs deferred to the long term. The generative move is splitting the conjunction. Ask which half you actually need, and a smaller mechanism than singleton serves it. A pattern's popularity measures its convenience. Its correctness is a separate measurement. This section explains the state pattern as a structural primitive. Boolean flags on the heroine, Anna's jumping flag, Anna's ducking flag, implicitly span a product space where most combinations are meaningless, and every new move multiplies the invalid region. The chapter's primitive is to make the state explicit, one variable ranging over a fixed set, with transitions keyed by input. The invalid region vanishes by construction, because the type now contains exactly the legal configurations. That is a finite state machine, and the Gang of Four state pattern is merely its object-oriented incarnation. Each state is a class owning its own behavior and data. The charge time field lives in the ducking state class and nowhere else. Nystrom's arc runs from flag soup through enum and switch to reified states. The machine stays the same while encapsulation increases. The constraint is the value, one state at a time, enforced structurally rather than defensively. This section explains the double buffer, a structural primitive. A double buffer is two copies of one piece of state held under a role invariant. Readers see only the current copy. Writers mutate only the next copy. And a swap, atomic and often a single pointer assignment, exchanges the roles when the write completes. The effect is that an incremental, sequential mutation becomes observationally instantaneous. No reader can ever witness work in progress. Nystrom's anchor is the frame buffer. The video hardware scans pixels while you draw them, and without the second buffer, the race prints itself on screen as tearing. His two-stage theater carries the same structure. One stage lit, one dark, where the stagehands work, the lights toggling per scene. The cost is exactly the doubling. Twice the memory, plus the swap on the critical path. This section is about the game loop and what it changes about the nature of a program. A game loop is a clock. It decouples simulated time from both user input and processor speed. Batch programs run once and stop. Event loops block until you act. A game loop spins regardless, process input without waiting, update one tick of world time, render a snapshot so the world keeps moving while you stare. The whole design problem is the exchange rate between two clocks, the machines and the worlds. Every variant Nystrom develops, whether sleep to sync, variable step, or fixed update with catch-up, is a different contract for that exchange. He calls it the one pattern the book couldn't live without. It is where a program stops answering you and starts existing alongside. This section explains the update method pattern at its structural core, which is a single inversion. The game loop takes ownership of behavior and slices it into frames. Nystrom's skeleton guard writes itself naturally as two for loops. Direction lives implicitly in which loop is executing. But that program never yields, so the player never sees a frame. Update method flips the arrangement. Each entity exposes one update method that advances its behavior exactly one frame slice, and the game loop iterates a collection it knows nothing about. The price is stated precisely in the chapter. Control flow state must be reified into data, a flag such as patrolling left, because a function that returns each frame cannot remember where it was. The pattern is essentially a manual coroutine, the compiler's stack frame, rebuilt by hand as member variables. This section explains the bytecode pattern, and behavior compiled to data is the whole pattern. A spell, a script, and AI routine becomes a flat byte array, instructions for a virtual machine you write yourself, which Nystrom shows is nothing more than a stack, a loop, and a switch statement. The move sits precisely between two failure modes. On one side sits the interpreter pattern's tree of objects, safe and sandboxed, but cripplingly slow, because pointer chasing murders the cache. On the other side sits raw machine code, dense, linear, fast, and a security hole. Bytecode keeps machine code's shape, contiguous, sequential, minimal ops composed. Meanwhile, the virtual machine's tiny instruction set is the sandbox, since the data can only do what you gave it verbs for. Flexibility of data, speed near code, trust of neither required. This section explains the subclass sandbox pattern at its structural core. The chapter's move is a coupling funnel. Give every subclass one abstract method, activate, to fill in, and let it fill that method using only the probed operations the base class provides. Play sound, spawn particles, nothing else. 100 superpower subclasses then touch the engine through a single membrane. The generative primitive, when many variants must each do arbitrary imperative things, shrink what they can call, rather than policing what they call. Nystrom names the symmetry worth keeping. This is template, method inverted. In template method, the base owns the method, and subclasses supply the primitives. Here, the subclass owns the method, and the base supplies the primitives. A type is shared data with a name, and nothing requires it to live in the compiler. Nystrom's move in Chapter 13 replaces hundreds of 7-line dragon and troll subclasses with 2 classes. Monster holds instant state. Breed holds what a whole kind shares. Each breed instance becomes a type. The type system migrates from compiled hierarchy into runtime objects. Designers mint new monster kinds from a config file with 0 recompiles, hundreds of breeds from one class. His footnote closes the loop. C++ already works this way. The vtable is a breed object, and the vtable pointer is the monster's reference to its breed. The pattern hand rolls machinery the compiler was hiding in exchange for owning it at runtime. This section explains the component pattern, the structural primitive that keeps one game entity from fusing all of its domains into a single class. A single game entity spans many domains: input, physics, rendering, sound. The naive move puts all of Björn the baker's behavior into one class, and that couples everything to everything. Nystrom calls this the Gordian knot, where touching physics demands knowing graphics. The component pattern cuts along domain boundaries. Each domain becomes its own component class, and the entity collapses to a thin container that merely holds them. Reuse then becomes pure composition, freed from the inheritance machinery. No deadly diamond, no bloated base class. Decoration, prop, and zone are the same game object with different components plugged in. His menu figure compresses it, monoliths sell combos, components sell a la carte. The entity is what it contains, nothing more. A cue decouples in time, what observer decouples in space. Nystrom's intent line carries the whole chapter. Decouple when a message is sent from when it is processed. That is chapter 15 in one sentence. A synchronous call, like his play sound calls sprinkled through UI code, forces the receiver to run on the sender's stack at the sender's moment, blocking the sender until it finishes. Insert a buffer of pending requests, and the sender returns immediately. The receiver drains the buffer at its own cadence, aggregating or dropping duplicates along the way. The buffer is the primitive. It converts control flow coupling into data, and data can wait. The cost is equally structural. The sender loses the reply and the shared present moment. State may have changed by the time the event lands. This section explains the service locator pattern. A service locator is a phone book for your codebase. Callers look a service up by its abstract interface, and a single registry answers with whatever concrete provider is currently bound. Nystrom's audio example, in chapter 16, shows the two couplings. The pattern dissolves at once who the service is, meaning the concrete, console audio type, and where it lives, whether a static class, a singleton, or anything else. Call sites end up bound only to the interface. The binding moves from compile time to runtime. That deferral is the whole pattern and its whole cost, since dependencies vanish from the code you read. Structurally, the locator is singleton, with the identity abstracted out, the same global access, but what sits behind it is now a slot whose contents can change, where singleton held one fixed object. This section explains data locality, the pattern that makes memory layout itself, the optimization. A cache miss costs hundreds of cycles. A register hit costs one. The chip fetches memory, a whole cache line at a time, 64 to 128 contiguous bytes, so the speed of your program is set by how much of each fetch line you actually use. Nystrom ran two programs performing the identical computation. One was 50 times slower, and the entire difference was cache misses. His conclusion in chapter 17, the way you organize data directly impacts performance. The pattern therefore moves optimization out of code and into layout. Place the things you process together next to each other in memory, and traversal becomes a run of cache hits. One boundary, this holds for a single thread. Two threads. Writing, one cache line, force costly cache, synchronization, and contiguity turns hostile. This section explains the dirty flag, a single bit that mediates between two representations of the same state. Primary data that changes cheaply, and derived data that costs something to rebuild. The flag records only that the two are out of sync. It is set on every write to the primary, checked on every read of the derived, and cleared after one recomputation. The move shifts work from write time to read time, so a burst of writes collapses into, at most, one rebuild per read. Nystrom's scene graph in chapter 18 with its ship, crow's nest, pirate, and parrot turns 10. Transform recalculations into 4, the provable minimum. He calls the move intentionally engineering a little slippage, deliberate staleness as an optimization primitive. The boundary is sharp. The flag pays only when writes. Outpace reads, and incremental update is hard. A running total beats a flag whenever you can pay as you go. This section explains the object pool, a pattern that decouples two lifetimes that allocation normally welds together, the lifetime of an object and the lifetime of its memory. A pool allocates one contiguous block at startup and never returns it. Objects are then created and destroyed purely by flipping an in-use state inside that block. The memory manager sees a single immortal allocation, so heap fragmentation cannot occur. That fragmentation is the slow shattering of free space into unusable slivers, which Nystrom in Chapter 9tation is the slow shattering of free space, which Nystrom in Chapter 19 called keeps its illusion of free churn. This is the same move as arena allocation and connection pooling. When acquisition is the expensive or dangerous act, amortize it once and recycle the artifact. This section explains the spatial partition pattern at layer 1. The pattern is one move, make the query key the storage key. The question of what is near this point is a lookup on position, so store objects indexed by position. A grid is the chapter's simplest form and the order n squared all. Pairs scan collapses into per cell work, each cell a mini battlefield. This is the database index idea transplanted into space. The one-dimensional case is literally sort, then binary search, and the pattern is its higher dimensional generalization. The cost is that the key is alive. A moving unit mutates its own index. Nystrom's image in Chapter 20 is a hash table whose keys change spontaneously, so every position update must refile the object. The pattern is worth paying for only when n and the query rate are both large.